Okay, so we are now live, part 23 of the Game Engine live stream, and this part 12 of the gestures. And give me a moment. Oops, it's easy. Okay, so as usual, we will start off with a page turn on Game Engine architecture, reading there out. So one page turn is equivalent to 2 pages. And here we go. That's what we usually do, is go into a brighter page, brighter screen, so it's easier to read. Okay, so obstruction freedom. An algorithm is obstruction free if we can guarantee that a single thread will always complete its work in a bounded number of steps. When all of the other threads in the system are suddenly suspended, a single thread that continues to run is said to be performing a solo execution in this scenario, and an obstruction free algorithm is sometimes called solo terminating because the solo thread eventually terminates while all other threads are suspended. No algorithm that uses a mutex lock or spin lock can be obstruction free, because if any thread were to be suspended while it is holding a lock, the solo thread might become stuck forever waiting for that lock, which is obviously bad. Lock freedom. The technical definition of lock freedom is that in any infinitely long run of the program, an infinite number of operations will be completed intuitively. A lock-free algorithm guarantees that some thread in the system can always make progress. In other words, if one thread is arbitrarily suspended, all others can still make progress. This again precludes the use of mutex or spin locks, because if a thread holding a lock is suspended, it can cause other threads to block. A lock-free algorithm is typically transaction-based. A transaction may fail if another thread interrupts it, in which case the transaction is rolled back and retried until it succeeds. This approach avoids deadlock, but it can allow some threads to stop. In other words, certain threads might get stuck in a loop of failing and retrying their transactions indefinitely, while other threads' transactions always succeed. Wait freedom. A wait-free algorithm provides all the guarantees of lock freedom, but also guarantees starvation freedom. In other words, all threads can make progress and no thread is allowed to starve indefinitely, which is good. The term lock-free programming is sometimes used loosely to refer to any algorithm that avoids blocking, but technically speaking, the correct term for obstruction-free, lock-free, and wait-free algorithms as a whole is non-blocking algorithm. The topic of non-blocking algorithms is vast and is still an open area of research. A complete discussion of the topic will require an entire book of its own. In this chapter, we'll introduce some of the basic principles of lock-free programming. We'll begin by exploring the true casues. Is that meant to be causing? Spelled incorrectly. I'm going to say causes of data race bugs. Then we'll have a look at how mutexes are actually implemented under the hood and learn how to implement our own inexpensive spin locks. Finally, we'll present an implementation of a simple lock-free linked list. This discussion ought to be sufficient to give you a flavor of what lock-free data structures and algorithms tend to look like, and should provide a solid jumping off point and further reading and experimentation with lock-free techniques. I want to see this because I think it's causes, but I want to see if casus is a word that I just don't know about. I mean, it's possible. No, it doesn't look like it from the little few second Google search I just did. Causes of data race bugs. Yeah, the actual section is that's what is called that. That was a misspelling. 4.9.1 Causes of data race bugs. In section 4.5.3.2 we said that data race bugs occur when a critical operation is interrupted by another critical operation on the same shared data. As it turns out, there are two other ways in which data race bugs can arise, and if we're going to implement our own spin locks or write lock-free algorithms, we'll need to understand them all. Data race bugs can be introduced into a concurrent program via the interruption of one critical operation by another, by the instruction rendering, reordering, optimizations performed by the compiler and CPU, and as a result of hardware-specific memory ordering semantics. Let's break these down a bit further. Threads interrupt one another all the time as a result of preemptive multitasking and all by running them on multiple cores. However, when a critical operation is interrupted by another critical operation on the same shared data object, a data race bug can occur. Optimizing compilers often reorder instructions in an attempt to minimize pipeline stalls. Likewise, the out-of-order execution logic within the CPU can cause instructions to be executed in an order that differs from program order. Instruction rendering is guaranteed not to alter the way in which two or more threads cooperate to share data, thereby introducing bugs in a concurrent program. Almost done. Thanks to aggressive optimizations within a computer's memory controller, the effect of a read and write instruction can sometimes become delayed relative to other reads and or writes in the system, as with compiler optimizations and OOO execution. These memory control optimization are designed never to alter the observable behavior of a single-threaded program. However, these optimizations can change the order of a critical pair of reads and or writes in a concurrent system, thereby preventing threads from sharing data in a predictable way. In this book, we'll refer to these kinds of concurrency bugs as memory ordering bugs. In order to guarantee that a critical operation is free from data races and is therefore atomic, we must ensure that none of these three things can happen. Okay, that's one page done. Feel like that page turn took a little while. I mean, page turn, not one page. So 2 pages done. Slowly we'll get through this book. Okay, so Kusa, Half-Life 1 says, Zup. Hey, what's up, Kusa? I saw you earlier on in the Lego live stream. I remember you was gonna ask a question in this stream. Did you manage to resolve whatever the question was? If not, what was the question? Okay, so let's open up the solution. So I remember yesterday, let me turn the controller on, we actually finished gestures, or we finished the 8 gestures that we were implementing, which were these. So happy that we finished these gestures. Super happy. That took a little while, to be fair. And today I want to look at this circular rotations. So okay, so we had gestures where you would, let's say, move your stick left and rotate up, or right and rotate up, left rotate down, right rotate down, down rotate left, up rotate left, up rotate right and down rotate right. So those sort of gestures, but they're just for like about 25% of the overall sticks area, or circumference. So what we want to do is detect when we are constantly just rotating the stick like that. And there's several use cases for that. You might have a game where you have to unscrew something, so let's say anti-clockwise, you have to just keep going like that. So we need to be able to detect that. This is where things get pretty interesting. Okay, so DJM Game says, hello, I am developing a game like a SimCity Classic. Who interested? Subscribe my channel, support the work. And when I get a bit of time, I'll check that out. Do love SimCity. Okay, I don't know how it would work with this stuff, if it would work at all. Let's try it. Let me try. Let's put clockwise. You know what, I'll just copy and paste this to be a lot quicker. Stop having the issue where it's not properly tabbing. I don't know what is going on. I feel like it's something to do with maybe one of these stuff. Nah, don't feel like it is, to be fair. I'm gonna Google it. Don't need to fix the Oculus software. Visual Studio tab not working. Tab. No, that's not it. Control M. That was the minimize. See, I can't tab for some reason. Or I can only tab as far as I guess it's meant to go. But well, that's strange now. The tabs, it's like, oh, that's annoying. That is, that tab isn't properly working. It's not VS Code I'm using Visual Studio. Okay, so go to text editor, it's saying. Text, let me pause this video. Text editor. And it said go to C, C++, formatting, C, C++, formatting. General, automatically okay. Don't know why got tab incorrectly. Okay, we're here. The reset pause could cause a bit of an issue. Oh, the clockwise rotation. Let's have a little drink. I need to go to the toilet. Be back in a second. I'm back. I also took a detour to the kitchen. Okay, so the clockwise pattern. Let's see what comes up. What game's that? Pixel Gun 3D. Clockwise Joystick Gesture. Ooh. Nope. Yeah. What stuff do they do for kids? Interesting. I'll give it a subscribe. Might be useful for a little cousin. You need to be able to listen as well. Khan Academy, the old classic. No, that don't really help us. How to do the implementation? We could potentially use trigonometry for this. Didn't use it for the other gestures. They weren't really needed. Let me implement a very, very rudimentary form of this. So we'll have a gesture. This is writing up just that. Herdingen says hello. It's been a while since you've been on the stream, Her. You know, a lot has gone on since, you know, you've been on. We got the 8 gestures implemented. We're looking at just a general clockwise rotation now. So we got all 8 gestures done. I did these 4 yesterday. I think I did these 3 the day before. Obviously this one took ages. But yeah, we got it done. Got these 8 gestures done. Let me update this. I'll do this color. 6 days to go. Nice, I know. So yeah, just trying to figure out how to do a general clockwise, and I don't mean a once clockwise, just you can start it anywhere and just basically keep rotating, and you'll just detect that you're going clockwise. Also, thank you for your suggestions regarding the structs for the gesture pattern, the gesture steps, basically having it almost like an animation with frames essentially. I guess that's what the steps are. Really helped a lot. Once we got the left one working, the others for the most part just fell in line. It's not the cleanest, it was just a bunch of else's, but it works. Yeah, all is working well with those 8 gestures. They all seem to be working very well. Obviously, potentially could tweak more with the timings, but I mean, really, it works well. If you try and do it too slow, then obviously it won't work. But that's just the timings, because we reset after X amount of time. But we don't want it too slow anyway. But that's, again, it's working. That's a non-issue. And we made a lot of it dynamic in here. So jack or magic numbers, and even the reset is calculated based on which value is where. It's pretty cool, to be fair. So the left stick orientation. I mean, no, not left stick. Let me make sure we got left. It is left stick, but it's the clockwise gesture. Let me pause this video. Okay. So how are we gonna do the clockwise gesture? Let me Google it. I'm just gonna literally put Unreal Engine detect joystick rotation. I would say if you're new to programming and stuff, I would, stay away from game engine development initially. My recommendation would be just learn, C++, learn some mobile stuff, learn some OpenGL, and just make some games first, get a grasp of how games work, then get on to game engine stuff. Once you got a reasonable grasp on how games start to work, also make sure you play games as well. That's also a very important part. But while you're playing them, think, oh, this is a for loop, or we could even implement this with an if statement, or blah blah blah. And also look at the faults in games as well, and think, okay, if they had just done this in coding, then obviously not always that simple, but if you try and get into that mindset, you'll really help when you actually start making a game engine yourself. Also, the stuff that they did well, be like, so they've clearly implemented an extra loop to make this smoother, or an extra few if statements to make it, more dynamic, for example. Exactly. Literally what just her said.
Tomatoes? Okay, the way our character's looking. Because you're getting the actual controller rotation and then setting Unreal Engine using a controller inside.
Ooh, interactive snow surface. That looks pretty cool. I'm literally just gonna put SFML. Hello. Thanks for the advice. I am the person who sent you a DM for making a geometry dash clone. Oh, hi. A game engine consists of so many different parts. Some are quite simple, some can be pretty difficult. Exactly, it's one of the things that I'm discovering here. I've done game engine stuff before, but stuff that you would think that is going to be difficult may not be, and stuff that you think is that's going to be easy, you like gestures, probably won't take too long. So like the concept is very simple. You can explain in seconds. You can start to understand almost the theory of it in seconds, but the implementation can be a bit awkward. This guy does. I don't like it when people I understand. Some people can be a bit lazy with their questions. Dude, answer questions on YouTube all the time, and people can be a bit lazy and vague. But not how you talk with the community. At least in my opinion, you should not be talking with your community like that. That's definitely no help. This is just a bunch of different game engines. I've never heard of Orcs before. I've been considering whether I was going to do some Allegro tutorials or not. Some game engine called Love. And libgdx. Been considering doing tutorials on that for a while. And Construct. See if Allegro is still in development. I thought though that's a bit old in development, but that's like some car. Obviously that's what it's named after. Again, I've gone off on a tangent here. Okay, so detect the rotation. Let me say math detect rotation. Trigonometry. What Nick was talking about last week. Potentially could look at it in sort of unit circle terms and split it up into quadrants. Okay, so to work out the angle, let me get up this. So let's have a look at working out an angle. So if we've got, it's so awkward that I can't actually write stuff on it. I can if I get my other, screen tablet thingy majiggy. Maybe just try and do freehand. So saw. Okay. Toa. So we have essentially let's redraw this. This is too awkward like this, so I'm gonna. Okay, what do you want to achieve with the clockwise gesture? All I want to achieve is being able to detect when you're just rotating it, and then, you know, based on that, we can have data of how many full rotations you've done, how many total degrees you've gone. I guess if you got the total degrees, and you can get the full rotation, that's the simple thing. But it's just about, if you're in a game and the game says turn your left stick counterclockwise to unscrew something, so you would go like that. So it's basically that gesture. So it's not definitively the start and an end, so it's a little different to what we've already done. I'm gonna switch over to my tablet. Pardon me. You will still be able to see I'm getting it out, and I'm gonna plug it in now. So Huey on. Tablet a Huey on. Tableto. 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 Okay, so let me check the video. That's the QA time. I was gonna say what's sort of with that. The webcam, the display capture. Okay. Okay, so let me zoom out a bit. Those are the only ones you can do, so let me grab a pen. So it is basically a gesture with 8 steps, where the start and position can be any of those 8 positions. Yeah, I guess we could look at it as 8 steps, to be fair. I guess there's no reason start and position can be any of those 8 decisions. I mean, those steps would almost have to be dynamic, or the start and end position would be, because you may not go move the stick to the left or never eat shredded wheat. So you, or you know, northwest, you might sort of go in between the two. So that's the reason I'm doing some trig here. Okay, so let's have a look, shall we? What we got? Have a look what we're dealing with. Yeah, this brush is tiny. Okay, so we will go to write out so Toa and we will, I'll put a different color for those lines. Let's put a brown color for the separation. So let's say if we have a center point and around it we draw a circle, and let's say if the user moves the stick over here, let's say this is minus 100, well, that is how it is, to be fair. Okay, so if we go to, let's say, a bluey purpley color, blue color. So ultimately what we know in this scenario is the x value. Let me undo that. And the y values. And let me pause this video again while it's started playing again. So those are essentially what we know when it comes to this. And let's say this is, I don't know, 50 in this scenario, and this is pretty high up. Let's say it's negative 90. So in this scenario we have x equals 50, y equals negative 90, and we don't want any other negative, so we'll convert y is equal to 90. So we can do a simple check to do that. We can basically check, is x or y less than or equal to 0, then multiply by negative 1. So that's not a problem. We multiplied it by negative 1. So now that we've got these, if we draw out the triangle, okay, so we have 50, 90, obviously not drawn to scale. We want to first of all work at the angle. Oh, no, we know the angle. That's 90. You want to work at this angle. So we have the adjacent and the opposite. Adjacent and the opposite, so it's tan. That's all really online, so probably will just be persistently be tan. So tan equals the opposite, so which is y, over x, which tan equals 90 over 50. Trying to extend this window is a bit awkward. That footstool. Confused again by the footstool, where the footstool was. Okay, so we get that. What is it? 10 to the negative 1 of 90 over 50 will give us the angle. So let's say in this scenario, if I was to do this, let's get out a calculator. Apparently comes up as 1.06, but I am in radians, to be fair. So it would help if I was actually in degrees. So that comes up as 60 degrees. I mean, that probably is about right. Anyway, so 60 degrees. So that would come up as 60 degrees. That's basically what we would get. So that's some basic tan stuff. So we got how to check the angle. And I guess we could say if the next angle we're probably still gonna need to do the quadrants, to be fair. The quadrant 1, 2, 3 and 4. So I'll have to use a form of a unit circle. I'll leave that there for now. Okay, so what I'm going to do now, I'm going to wrap up this stream for today. We really haven't done any coding, but we've done a fair bit of theory, some basic high school maths to help solve the problem, and that's what it's all about. Just progressing, even if it's just a matter of testing a bunch of things and determining, okay, that's not the way to go, and just failing. That is fine. So if you have any questions, let me know, because I'll be ending the stream in a few minutes. This is a short one, I know, but I will be doing another one tomorrow, and we'll look at but implementing this feature. So let me know if you have any questions. Okay, I need to sort out this as well. Boom, there we go. Okay, so I'm just gonna wait till probably a couple more minutes, and then we'll see if we've got any questions. If not, then I will be ending the stream. But yeah, let's wait and see if anyone has any questions. I'm gonna wait one more minute, and we'll see if anyone has any questions. If not, I will wrap up for today. Let me build this. Make sure we're getting no errors. Waiting to see if anyone has any comments, any questions. We're looking very quiet today, so I'll be ending the stream very soon. When it gets to 16 minutes past, then I'll end the stream. Okay, so I'm gonna end the stream now. Thank you for watching. Be doing another one tomorrow, where we'll hopefully be implementing some of this basic trigonometry maths that we just looked at, the TOA stuff. So thanks for watching, and I'll see you tomorrow, and have a good day, good evening, good morning, and good night, or wherever you are.